Hello guys, welcome to Collegewali PADHAI. So today we are at episode 4 of chemistry in which we are going to discuss molecular orbital diagram of some compounds. Then we are going to discuss aromaticity, Huckel's rule and some of the benzene and all those stuff, aromatic, non-aromatic, anti-aromatic. So stay tuned and watch the video till the end. Let's get started. So first, let's move towards the molecular orbital diagram. So this is basically I had written in all these in the copy, so it was better to take a snap and convert into PDF and show. So basically, C has electronic configuration 1s2, 2s2, 2p2. It is written 1s2, 2s2, 2p2, and O has configuration 1s2, 2s2, 2p6, 2p4, sorry, it's written 1s2, 2s2, 2p4. So the first one is having non-bonding, second one it has already made 4, 1, 2, 3, 4 because 2 plus 2, 4. Then the third one has to make 6. So this is the pi bond, sorry, this is the pi bond, these two are the pi bond, this is the sigma bond. This is pi star anti-bonding. This one is the sigma star anti-bonding. So first we have to place 1, then 2. How many are remaining? More 4, 3, 4. Another 2 are remaining here. Done. So first we have, it has non-bonding, 1s2. 2s2, 2s2 it is 4. So it has already made 4. Then 2p2 and 2p4 it is 6. So in the pi bonding it has made 4 and in the sigma bonding it has made 2. 4 plus 2 6 and the anti-bonding orbitals are empty. So the pi bond which you are seeing this part, let me change the color, blue. This part which you are seeing it over here, this part and this part, as they are completely filled, so they are called as homo means highest occupied molecular orbital. Let me write highest occupied molecular orbital. And what you are seeing over here, this part, this pi star, sigma star, that is called as LUMO. That is lower unoccupied molecular orbital. So this is the molecular diagram of carbon monoxide. Now let's see the molecular diagram of butadiene. So we will move from the bottom part, butadiene. So this is pi 1. We have to draw cones on opposite sides, and this one is colored portions, that zigzag you are seeing. Then bond here is made and nodes are 0. When it is coming to pi 2, here both are filled, here both are filled. So it has nodes 1 and it is called, when the node is 1 it is called as HOMO, highest occupied molecular orbital. When the node is 2 it is moving like this. Are you seeing the shape like this? When the node is 1 it is going like this. And when the node is 3 it is making a shape like this. irregular shape, just like this. Here it is shown. Here one bond, here one bond. It is the 4 electron system. And remember that in one node 1 it is making highest occupied molecular orbital, and in node 2 it is making lowest unoccupied molecular orbital. You can take a screenshot or slow down the video and see. So while talking about aromaticity, let's start with benzene. Benzene is C6H6. We have shown here it's benzene, and I have also drawn its diagram also. It's just a value, means it has 1.3 angstrom, 1.3 angstrom. So it has 6 carbon, and it is going in the sequence double bonded, then single bonded, then double bonded, then single bonded, and each carbon is attached with a hydrogen. So 6 carbon atoms with 6 hydrogen. And here it shows a 3D diagram which I have drawn with the help of pen, so it is not clear. Actually, these are the pi electrons. These are the pi electrons which are delocalized around the ring above and below the plane. What are these? These are pi electrons which are delocalized around the ring above and below the plane. So then I would request you to see the molecular orbital diagram of benzene from Google, as I have not made it clear. I would request you to see this part from Google, or else if you want, then I can make a separate video on it. So skip this. Then let's come to Huckel's rule. So what is Huckel's rule? The rule that is based on mode treatment and is employed for predicting what aromaticity of organic compounds. So how can you remember Huckel's rule? Huckel's rule is based on mode treatment, and Huckel's rule is employed for predicting aromaticity of organic compounds. So definition you must learn. This is the definition. Then let's move to requirements. So the molecule or the ion must be a flat shape. Molecule or ion must be flat shape. It must contain cyclic clouds of delocalized pi electrons above and below the plane. Same. There in benzene we saw what? Pi electrons are delocalized around the ring above and below the plane. But in Huckel's rule, the requirement is that it must have cyclic clouds for delocalized pi electrons above and below the plane. Then the pi electrons in the cloud must have a total number of 4n plus 2 pi electrons. You must remember this most important sentence. This is the most important point. The pi electrons which are present in the molecule must have a total of 4n plus 2 pi electrons. This must be remembered. Then you know that above requirement was for Huckel's rule, or it is also called as 4n plus 2 rule. And the Huckel's rule is for cyclic polyenes or polycyclic. What I will repeat, okay? So the above requirement is for Huckel's rule. Huckel's rule is also known as 4n plus 2 rule, and these can be used for cyclic cyclic polyenes and polycyclic. And those who have pi electrons are aromatic, and those do not have that are non-aromatic. So let's again take a revision of Huckel's rule that is based on mode treatment and is employed for predicting aromaticity of organic compounds. Simple definition done. Then requirements, the molecule or ion must be flat. Then it must have it must have cyclic clouds of delocalized pi electrons above and below the plane. Done. Then third one, the pi clouds in the molecule must have a total number of 4n plus 2 pi electrons. Then the above requirements are for Huckel's rule, or it is also known as 4n plus 2 rule, and these are for cyclic polyenes and polycyclic. Those who have pi electrons, they are aromatic, and those who do not have, they are non-aromatic. Then this is how benzene is drawn. You must have known in class 11th and 12th, you must have drawn thousands and thousands of benzene diagram. But you must not have known that benzene has 6 pi electrons. One over here, 1, 2, 3, 4, 5, 6. Benzene has 6 pi electrons. Then let's move to naphthalene, which has 10 pi electrons. The structure of naphthalene is somewhat like this. Here it is 1, 2, then here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Then anthralene, we saw benzene, we saw naphthalene, then we are now seeing anthralene. Anthralene is somewhat like this: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So it has 14 pi electrons. Just remember that benzene has 6 pi electrons, and naphthalene naphthalene has 10 pi electrons, anthralene has 14 pi electrons. And do remember the diagrams. Then pyrene, pyridine. Pyridine is somewhat like this. Same means here we have to draw the structure of a benzene just like this. Then here one, here one, here one, then here n, lone pair upward, lone pair downward. It has pyrene, it has 6 pi electrons, just like benzene. Pyridine is over. Now it's the time for pi mole. Pi mole is same, but here the structure is different. Like this, we have to draw. Then NH, and above N, two lone pair must be there, and here parallel. Both these two must be parallel. It also has 6 pi electrons. Then furan also has 6 pi electrons. Same structure as that of pi mole, and these two must be parallel. Oxygen must be there, and above oxygen two lone pairs. Thiophene is what? Thiophene is same structure, and in place of oxygen over here it must be S, and above S and below S must be lone pairs, and these must be parallel. It also has 6 pi electrons. And then cyclopropanyl cation is what? You have to just draw a triangle over here and increase this H, and here plus sign, here a baseline. So it has around 2 pi electrons. Just make a triangle, extend the right hand side of the line, place a positive sign over there. So it is called as cyclopropanyl cation. Then cyclopentadienyl anion. So this one is the cyclopentadienyl anion, in which the both diagrams are same, but here hydrogen is extended. Means lone pair along with a negative sign is placed in both the diagrams. But in the first diagram, the line is extended and a hydrogen is placed over here. And these are also the same. These are all of these. So it has cyclopentadienyl has 6 pi electrons, and it or has structure is same but positive sign, and another one with a dot. It has 4 pi electrons and it has 5 pi electrons. So how can you define whether a structure is aromatic or non-aromatic or anti-aromatic? Anti-aromatic. So if the remaining hydrogen, if hydrogen is remaining at the end of the chain that can be together formed as a ring, and that ring has pi electron energy less than that of open chain, then it is aromatic. So I have written here less pi electron energy than open chain, then it is aromatic. But if the pi electron energy is equal to open chain, it is non-aromatic. And if the pi electron energy is greater than open chain, it is anti-aromatic. So what we knew, if the remaining hydrogen at the end of the chain together forms a ring in which the pi electron energy is less than that of open chain, then it is aromatic. But when the pi electron energy is equal to open chain, then it's non-aromatic. And if the pi electron energy is greater than open chain, then it is anti-aromatic. Process is same, just 3 cases are there. Case 1, case 2, case 3. Then at last, aromatic, anti-aromatic, non-aromatic differentiation. These two are most probably same as cyclic, cyclic, planar, planar, conjugated, conjugated, but the last part is it has 4n plus 2 pi electron and it has only 4n pi electrons. So if this condition as well as this condition fails, then it leads to non-aromatic. Means if both aromatic and anti-aromatic condition fails, then this will lead to anti-aromatic. So at last, at the end of the video, I would like to thank all the viewers who have watched the video till the end. This was just to give you an idea about molecular orbital, what is aromaticity, Huckel's rule, aromatic, anti-aromatic and non-aromatic. So if you liked the video, do subscribe to the channel, press the bell icon for more updates and share with your friends to learn more. Thank you.